Does the universe have an edge? It sounds like a simple question, but the answer is surprisingly subtle. If by universe we mean everything that exists, then by definition there is nothing outside it to form an edge. In other words, the universe has no outer fence or wall. It may instead be like a balloon or a paper sheet that either wraps around itself or stretches on forever without border. As one science writer puts it, the universe does not have an edge in any physical sense. The only edge we can really define is the observable horizon, the limit of how far we can see. Observations from the cosmic microwave background, supernovae, etc., suggest space is flat on large scales, meaning it extends without bound like an infinite sheet. Even if it were slightly curved and finite, like the surface of a sphere with nothing outside it, there would still be no abrupt end. You just eventually come back to where you started. What we can see is limited by the age of the universe and the speed of light. Since light takes time to travel, we only receive light that has had time to reach us since the Big Bang. Cosmologists call the region of space we can, in principle, observe the observable universe. This is a spherical volume centered on us, containing all galaxies whose light has reached Earth. Calculations show it spans about 93 billion light-years in diameter, roughly 46.5 billion light-years radius. How can this be when the universe is only 13.8 billion years old? The reason is that space itself has been expanding. Light from a galaxy that left 13.8 billion years ago has been stretched and carried away, so that galaxy is now about 46 billion light-years away, even though its light just arrived today. Beyond this observable sphere, there are undoubtedly more galaxies, possibly infinitely many, but their light hasn't had enough time to reach us. An important consequence of the finite speed of light is that we see the universe as it was, not as it is right now. Every star, galaxy, or quasar we observe is seen at some point in its history. For example, the sun's light takes about 8 minutes to reach us, so we see the sun as it was 8 minutes ago. Even the nearest stars are years away, and the most distant galaxies we have ever seen emitted their light billions of years ago. As one astronomy writer puts it, the time it takes for light from objects in space to reach Earth means that when we look at planets, stars, and galaxies, we're actually peering back in time. In fact, our most powerful telescopes, like Hubble and JWST, act as time machines. The Hubble Extreme Deep Field shows galaxies as they were about 13.2 billion years ago, only 0.6 billion years after the Big Bang. In short, today's universe is invisible to us. All we see is the historical light. The farthest light we can ever see is the cosmic microwave background, CMB, released about 380,000 years after the Big Bang. That light has been traveling for 13.8 billion years, but because of expansion, its source is now about 45 to 46 billion light-years away. We call this the particle horizon or cosmic horizon, a hard limit of sorts on our observations. However, it's not a real fence in space, just like the horizon at sea is not a solid wall. As the Sky and Telescope writer notes, the cosmic horizon is much like an ocean horizon. Just as we know there's more ocean over the horizon, we know there are more galaxies beyond the cosmic horizon, whose light simply hasn't reached us yet. Technically, cosmologists distinguish several horizons: particle horizon, event horizon, etc. But intuitively, you can think of the cosmic horizon as the size of the observable universe. Anything beyond that is unobservable for now. The cosmic microwave background is literally the oldest light we can see. It fills the whole sky as a faint microwave glow at about 2.7 kelvins. Astronomers believe this radiation was released about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral atoms, making the universe transparent to light. Before that, the universe was a hot, opaque plasma, so photons were trapped. When the photons finally escaped, they have been traveling ever since, stretched by expansion into microwaves. This afterglow carries tiny ripples in temperature, 1 part in 100,000, which are the seeds of today's galaxies and clusters. The CMB was predicted on theoretical grounds in the 1940s by Gamow, Alpher, and Herman, who reasoned that the Big Bang must have left behind residual heat. It was discovered serendipitously in 1964 by Arno Penzias and Robert Wilson, earning them a Nobel Prize, as a persistent microwave hiss with no obvious source. Since then, missions like COBE, WMAP, and Planck have mapped the CMB across the sky, confirming it is a nearly perfect blackbody at 2.73 kelvins with slight fluctuations. Is the universe flat, open, or closed? One big question is the overall shape of space. According to general relativity, space can be positively curved, negatively curved, or flat, depending on its total energy density. These correspond to three idealized geometries: closed, positive curvature. If the average density of matter energy exceeds a critical value, space is curved like a higher dimensional sphere. In this case, parallel paths would eventually converge, and a long trip in one direction could bring you back to your starting point. The universe would be finite, though unbounded. Like the surface of the Earth has no edge even though it's a finite 2D surface. Open, negative curvature. If density is below critical, space has a saddle, hyperbolic shape. Parallel lines diverge and the universe is infinite and unbounded. If density is exactly at the critical value, space is flat like a sheet of paper. In that case, Euclidean geometry holds on cosmic scales, and the universe is infinite, again unbounded. Which do we live in? Multiple observations, especially detailed maps of the CMB by WMAP and Planck, show that we are extremely close to flat. WMAP found that the angles of CMB fluctuations imply a flat universe to within about 0.4% uncertainty. Only about 5% of the universe's mass energy is ordinary atoms, the stuff of stars, planets, you and me. Roughly 27% is dark matter, an unknown form of matter that does not emit, absorb, or scatter light. Dark matter is literally invisible, but it exerts gravity, and in fact, it dominates the gravitational mass in galaxies and clusters. NASA describes it as the invisible glue that holds the universe together. Dark matter is needed to explain a host of observations. Stars and galaxies orbit too fast to be held by visible mass alone. Galaxies and clusters move with excess velocities, and gravitational lensing of distant light shows more bending than visible mass can account for. In the 1970s, Vera Rubin measured the rotation of spiral galaxies and found the outer stars whipping around as fast as inner ones, again requiring extra mass to hold the galaxies together. These missing mass clues convinced astronomers that most of the matter in the universe is dark. Although we still don't know what dark matter is, many candidates exist, from exotic particles to primordial black holes. We know it must be cold, slow-moving, and only interacts gravitationally. Its gravitational influence creates the scaffolding for structure. Galaxies form along the dense filaments of dark matter. For most of the 20th century, astronomers assumed cosmic expansion should be slowing under gravity. But in 1998, two teams of astronomers made a startling discovery. Observations of distant Type 1a supernovae showed they were dimmer farther than expected in a decelerating universe. The supernovae teams, led by Reese Schmidt and by Perlmutter, found over 50 distant exploding stars whose light was fainter than the models predicted. The only conclusion was that the expansion of the universe is actually accelerating. This discovery, so surprising that it earned the 2011 Nobel Prize, implied a repulsive component to cosmology dubbed dark energy. Today we know dark energy makes up about 68 to 70% of the universe's total energy budget, pushing everything apart. NASA notes that about 9 billion years after the Big Bang, the expansion began to speed up under this unknown force. Since our cosmic horizon is just the limit of sight, it's natural to wonder, what's out there beyond? The simplest answer is more universe, probably much like the part we see. Theories like inflation suggest space expanded uniformly, so it's reasonable that distant patches contain more galaxies and gas. If space is infinite, then beyond the observable sphere there are infinitely many more galaxies. We just can't see them yet. Beyond our horizon, we might have regions with slightly different compositions or fluctuations, but no fundamental reason to expect a sudden change at the 46 billion light-year mark. We also have to keep in mind the universe's center of expansion is everywhere, so the notion of beyond is relative. One wild but popular hypothesis is that our universe might be just one pocket in a larger multiverse. In this scenario, the Big Bang was one inflationary bubble, and other such bubbles could nucleate with different physical constants or laws. This idea comes from eternal inflation and other high-energy theories. Some cosmologists have a response. Our universe is a swelling bubble. Outside it, more bubble universes exist, all immersed in an eternally expanding sea, the multiverse. Beyond our cosmic horizon could be neighboring universes. They might be forever inaccessible to us. They have their own expanding space and horizons. But they are a logical possibility if inflation is correct. Perhaps only some bubbles, like ours, allow stars and life. This bubble multiverse picture is speculative and hard to test, but it's a way that physicists explain why our universe has the precise conditions we observe and how physics might permit many different outcomes. What happens to our cosmic horizon as the universe keeps expanding? If expansion continues to accelerate, as observations suggest, distant galaxies will become unreachable and dimmer. According to cosmologists, eventually the universe will approach a steady de Sitter expansion. In that regime, an event horizon forms, a distance beyond which objects can never reach us, even at the speed of light. Currently, light from regions beyond about 60 billion light-years, co-moving distance, will never reach Earth, no matter how long we wait. NASA physicist Adam Rees and colleagues have noted that accelerating expansion will make all galaxies outside our local group fade and recede beyond the horizon. In effect, most of the universe will become unobservable. In fact, astronomer Ethan Siegel points out that already about 94% of galaxies, those currently beyond approximately 18 billion light-years, are destined to remain unreachable by us, even at light speed. Looking far into the future, scientists have devised a few scenarios for the ultimate fate of everything, based on the nature of dark energy and cosmic content. Big freeze. This is the standard outcome if dark energy is a constant vacuum energy. The universe will expand forever, galaxies will drift apart, and star formation will cease as galaxies run out of gas. Entropy will increase until all energy is evenly spread out. In practice, galaxies fade away, black holes evaporate, and the cosmos becomes a cold, dilute place. Big rip. In some theories, dark energy's repulsive force could grow stronger over time. In that case, the expansion could eventually tear apart galaxies, stars, planets, even atoms. The pull of the universe's expansion gets stronger than the gravity it contains. This would tear apart galaxies, followed by black holes, stars, and even our own planet. In extreme models, this happens at a finite time in the future when dark energy dominates all forces. Big crunch or big bounce? If, contrary to current evidence, the expansion were to reverse, for example, if dark energy decays or the universe's density were above critical, the universe could recollapse. All matter would fall back together, eventually collapsing into a hot singularity, essentially the Big Bang in reverse. Some speculative models even have a cyclic universe that bounces back and forth between expansion and crunch. However, current data, flat geometry, and positive dark energy make a big crunch very unlikely. To date, observations favor the big freeze. Thanks for watching.